So it's time to actually finish stoichiometry. This is the very last connection to stoichiometry that you're going to experience this year. Just take a second to celebrate that. So now that we know that we can measure heat, particularly for a chemical reaction, and we know that we have these values called molar enthalpies, which relate the number of joules to a number of moles, that honestly is going to signal a pretty clear connection to stoichiometry. Anytime that you're dealing with units of moles, anytime that you're dealing with a chemical reaction, stoichiometry is possible. And since heat is yet another untapped measurement, it's time to throw that into the stoichiometry realm. So again, molar enthalpy, or delta H, is almost similar to having like a molarity or a molar mass, in that it kind of relates your number of moles to a defined measurement. So it's a way of converting between the two. Delta H, because its units are in joules or kilojoules per mole reaction, could really be presented in one of two ways, just like molarity or molar mass would be. So you can have joules over moles reaction or moles reaction over joules, whichever the case is going to be more helpful to you solving your particular problem. Let's take a look at what this might look like more based in kind of a stoichiometry style of problem. So let's say you are given the measurement of joules, and you're going to start a stoichiometry problem. So you would start off with those joules going over 1, and then of course joules would cross down to the bottom of the next box, and your objective in this next step would be to convert to moles. In this step, just like molar mass or molarity, we can apply the delta H for this particular chemical reaction. Delta H gives us the relationship between joules and moles. It's just to moles reaction, but it still is a way into stoichiometry. After that, you could apply the mole-to-mole ratio and continue forward with your problem, however that needed to end up. Well, let's say that instead of starting with joules, our problem asked us to calculate 2 joules. So you would need to, have some other way of getting into that mole-to-mole ratio. Let's say, for example, you had grams. So you would use the molar mass to convert to moles. And then in your mole-to-mole ratio, this is probably the most important thing of this entire segment. You're going to have moles of that one specific chemical down to the bottom, and up to the top, you want to relate it to moles reaction. Now remember, when we've been talking about moles reaction, that's the entire chemical equation. And since the entire chemical equation represents moles reaction, the number in front of it is always going to be a 1. So it's always 1 mole reaction. Now the moles of the chemical underneath that could be different. That depends on the coefficient that's in front of that specific chemical in the balanced chemical equation. After this, what we'd be able to do is allow moles reaction to cross down to the bottom of the next box and be replaced with joules up top, applying delta H in this other form at the end of the problem, joules over moles reaction. And if I would solve the problem at this point, because joules are in the top last box, joules would be the unit that I should be expecting on my second measurement. I want to kind of show you how this fits into the overall grand scheme of things. You saw this chart last chapter as we were starting to knit together solids, liquids, and gases. Heat is the final type of measurement that I can take, so it's important to knit this all together in one nice little bow. So heat, its measurement is joules. You can always start with that going over 1. And in order to convert to moles, you would have moles reaction on the top and the delta H number for joules on the bottom. After the mole-to-mole ratio, that ratio would flip. Delta H goes to the top, moles reaction to the bottom, and out the back end of it, you would get joules. Now, just to kind of remember that there are now 5 different pathways into the mole-to-mole ratio, which makes the state symbols on the inside of your balanced chemical equation excruciatingly important, because they're actually going to tell you how to do your stoichiometry. You just need to simply pick one of these pathways forward. Any one of them, whether it be molar mass, using the molarity, the STP molar volume, 22.4 liters. Now remember, STP and standard molar volume are not the same thing. STP is 1 mole of a gas at 1 atm of pressure, 273 Kelvin, or 0 degrees Celsius. Standard molar volume means that at STP conditions, 1 mole of the gas takes up 22.4 liters. Or maybe the gas is not at STP, and then finally, of course, joules, which are super duper important. And of course, because there are now 5 pathways into the mole-to-mole ratio, there are 5 pathways back out, and they're just the inverse of everything that we just went over. So time to look at a sample problem. A 2.5 gram sample of sugar, C6H12O6, is burned in excess oxygen gas. How many joules of energy would be generated during the reaction? The molar enthalpy of the reaction is negative 20, or I should say 2,816 kilojoules per mole reaction. Well, if you know that we're talking about a chemical reaction, the first step should be, I'm hoping you're all saying it before I am, to write the balanced chemical equation for the burning of oxygen, the combustion reaction of this C6H12O6. So here she is. And notice what I tapped down at the side there. The delta H. This is a thermochemical equation. They gave me the thermo part right in the actual problem at delta H equals negative 2,816 kilojoules per mole reaction. So you might as well just report it right there, because that's how we're going to know whether or not heat is involved with our chemical reaction. So let's layer the information that we know. We have 2.5 grams of sugar, so I put that underneath the C6H12O6. And then finally, we're asked about the amount of energy, so I put that way over underneath the delta H value. What that lets me know is that I need to start with the C6H12O6 number in grams, and then I need to end with the number of joules. So these two factors are going to be playing a very important role in my overall chemical equation. Time to start setting up our stoichiometry. We'll take that 2.5 grams, we'll plop that over 1. Grams should cross down to the bottom of the next box, and that's the molar mass, converting it up to moles. Now time for the mole-to-mole ratio. Don't forget, when heat is involved, we need to make sure that we're converting to moles reaction. So moles C6H12O6 have fallen to the bottom, and there is only one equation listed on the page, so that's 1 mole reaction. Now we can apply the delta H number with moles reaction to the bottom, and the delta H number, negative 2,816 kilojoules up to the top. Time to plug and chug. The fewest numbers given to me in the problem as far as sig figs were 2, with 2.5 grams. So I'm going to limit my final answer to 2 significant figures. And in my calculator, I calculate negative 39 kilojoules. Now that negative symbol is kinda important. What this actually indicates to me is that the reaction is exothermic and that we're going to be losing 39 kilojoules of heat energy. Well, let's take a look at a similar but not quite the same problem. Let's flip-flop it around a little bit. If we wish for 500 kilojoules of heat to be released from the combustion of sugar, which is C6H12O6, how many grams of sugar would be needed? The molar enthalpy of reaction is negative 2,816 kilojoules per mole reaction. Again, don't go any further. If you know that there is a chemical reaction involved, write its balanced chemical equation. And that's going to look a little something like this. Notice it took the time again to write the thermochemical equation, showing the delta H symbol right behind it. Next step, layer in what you know. I know that the problem has given me 500 kilojoules of heat energy. And notice that as I layered it underneath, I turned that into negative 500. They told me that the heat is being released. That means the heat is being lost. It's exothermic. So I added in the negative sign. We are also asked about the grams of sugar, so I put question mark grams underneath the C6H12O6. Time to start our stoichiometry. We know that we need to start with the number given, that's the negative 500 kilojoules, and we know that we need to end with grams of C6H12O6. So let's start our stoich. Layer in the number that you know, negative 500 kilojoules over 1. Kilojoules has to fall down to the bottom of the next box, and we have to convert it into moles somehow. That relationship is given in the problem as negative 2,816 kilojoules for every 1 mole reaction. Time for the mole-to-mole ratio, where moles reaction are going to fall down to the bottom, always 1, and you can relate it to moles of a specific chemical up top, in this case C6H12O6, and that number in front of it, although invisible, is a 1 as well. And now finally, time to convert away from moles back into the measurement that they want, which is grams, and I'll get to apply my molar mass one more time, 180.16 grams for that sugar sample. I'm going to quick scan my problem for significant figures, and I find the fewest is contained in the original 500 kilojoules that they gave me. Notice that there's no decimal point, so those trailing zeros do not count as significant figures. That's one sig fig. So whatever I calculate here, I'm going to round it to one significant figure. And once I went to my calculator, it looked like it was approximately 30 grams.